Okay, this is the solution for quiz 8, chapter 8 on rotational motion. First, calculate the net torque acting about the point C, perpendicular to the page. So I have through that point, I'm going to look at two different torques. This force provides no torque because the moment arm equals 0. At this point, the torque acts, let's see, what's that, counterclockwise, so I'll call that plus torque 1. And this one acts in a clockwise fashion, so I'll call that minus torque 2. So my net torque then is going to be torque 1 minus torque 2. That's that force, 25 newtons, times r, which is the distance to the axis of rotation, which is 2 meters, times the sine of 45, minus torque 2, which is going to be 20 newtons, times 2 meters, times the sine of, what's that, 20 degrees. That's 50 sine 45, minus 40 sine of 20. Now I get a positive 22 Newton meters. Since it's positive, that's counterclockwise. So C is the right answer. Chad stands on a 5-meter long board. Blah, blah. Kai's has a mass of 60 kilograms. Where can she stand? Well, since she has a smaller mass than he does, there's really nowhere for her to stand. She would have to stand over here somewhere at some distance. But since the board doesn't go that far, she cannot balance the board. All right, here I want to know what is the moment of inertia for this configuration. Each of these balls has a mass of 1 kilogram, and this distance is 1 meter, so that means this distance is 0.5 meters. Each ball contributes the same moment of inertia. That's going to be mr squared. I want to know it for all 4 balls. That's going to be 1 kilogram times 0.5 meters squared. And since there are 4 balls and they are all the same, I'm just going to multiply that times 4. That's 1 kilogram times a quarter times 4 is 1 kilogram meter squared. So D is the right answer. Okay, I have a 100 kilogram merry-go-round of a radius of 1 meter, start from rest by a constant horizontal force of 50 newtons. Applied tangentially, what is the angular speed? So I want to know omega. I know that omega is equal to omega naught plus alpha t. Omega naught I know is 0 because it starts from rest. So I need to find out what alpha is. I know that alpha is the torque over the moment of inertia. So now I need to find the torque, which is equal to Fr sine theta. And I need to know I. This is for a cylinder or a disk. And if you look on your table, that's 1/2 mr squared. All right, so first the torque. The angle theta is 90 degrees, so sine of theta is equal to 1. My force is 50 newtons times the radius, which was 1 meter. It's going to be 50 Newton meters. And then my moment of inertia is going to be 1/2 times the mass, which is 100 kilograms, times the radius, which is 1 meter squared, so that's equal to 50. Now that gives me an angular acceleration equal to 1 radian per second squared, 50 over 50. And then I want to know omega after 3 seconds. So that's going to be my 1 radian per second squared times 3 seconds, be 3 radians per second. So A is the right answer. I have a merry-go-round, mass of 100 kilograms, radius of 1 meter, spinning at 2 revolutions per second. Then a kid jumps on. I want to know what is the new angular velocity. So this is going to be an angular momentum problem. I know that I initial, omega initial will equal I final, omega final. I have this disk. It's rotating around at 2 revolutions per second. It has a certain moment of inertia. That's going to be my I initial. It's a disk, so it's 1/2 mr squared. Actually, I think it's the same as the previous one. Yeah, 100 kilograms, 1 meter. So it's 50 kilogram meters squared. So that's my initial moment of inertia. So I'm going to put that in here. 50 kilogram meter squared times 2 revolutions per second. Notice I didn't have to change the units on this. I'll show you why in just a second. And then I have my I final. So I have this kid. He jumps on, and he has a mass of 50 kilograms. I treat him like a discrete particle. So he's like this particle that's moving around out at a radius of 1 meter. And his moment of inertia is going to be mr squared, which is 50 kilograms times 1 meter squared, which is 50. So my new moment of inertia is going to be 50 plus 50. The moment of inertia of the disk, the moment of inertia of the kid, times omega final. My moment of inertia increases by a factor of 2, so that means omega final decreases by a factor of 2. So it's 1 revolution per second. Notice that the units here, these cancel, kilogram meter squared, just leaving revolutions per second. That's what I want the answer in. Oh, it's not D, sorry, it's D. 1 revolution per second. All right, two spheres of the same radius, equal masses. One is solid aluminum, the other is a hollow shell of gold. Gold is higher density than aluminum, so you can have this hollow shell that has the same mass as a solid sphere. Which has the bigger moment of inertia? Well, moment of inertia is defined as mr squared, the sum of mr squared. So the one with more mass at bigger radii will have the larger moment of inertia, and that's going to be the gold. Okay, and this one, a figure skater pulls her arms in. When she pulls her arms in, she reduces her rotational inertia and spins faster. So if I think about this in terms of angular momentum, L, I omega, by pulling in her arm, she is decreasing her I, and so she increases her omega by the same amount. And then I want to know what happens to her rotational kinetic energy. Well, I know that kinetic energy is 1/2 I omega squared. I'm decreasing her moment of inertia, and I'm increasing her angular speed by that same amount. So if I imagine, that I decrease my moment of inertia by a half, that means that I have to increase my angular speed by a factor of 2 because of this relationship for angular momentum. And that says then that, notice I have a factor of a half here, but I have a factor of 4 here. So that means that my total kinetic energy has increased. So the answer is going to be B, that it is larger because she's rotating faster. And that extra kinetic energy comes in when she brings her arms in, that she's actually doing work on her arms to bring them in, and that causes her to spin faster. It increases her kinetic energy. Two different spinning disks of the same angular momentum, but disk 1 has more kinetic energy than disk 2. So I is the same for these. I1 is equal to I2, but the kinetic energy of disk 1 is bigger than the kinetic energy of disk 2. That means, just like we did before, that kinetic energy of disk 1 has a bigger omega than disk 2. So omega 1 is bigger than disk 2. That's because of this relationship between 1/2 I omega squared, that if I have a big omega, then that's a bigger impact because it's squared than is the moment of inertia. So if disk 1 has a bigger omega, that means it has a smaller moment of inertia. So disk 1 is the right answer here. All right, 4 T's are made from identical rods of equal mass and length. Rank in order moments of inertia. So what I'm looking here for is the one with the most mass at the biggest radii, with of course the idea that the radius is the bigger impact. So this one has a full rod at the largest radii, and so it has to have then the largest moment of inertia. So IA is the biggest, so it gets rid of this one and this one. And then let's see which one's the smallest. This one has a rod that only goes out to R/2, and this rod contributes nothing to its moment of inertia. So IC is the smallest, so that gets rid of C. So I'm now just left with D and E. So which one is bigger, B or D? Well, for B, this part of the rod contributes nothing to the moment of inertia because it's on the axis of rotation and R equals 0. So otherwise, it's identical to D. So D then is going to be bigger than B. So option D is the right answer. All right, this student holds a meter stick. as here. I just want to rank it from the most difficult to least difficult. We can just look at our torques. If we consider this 1 meter, I'm just going to take the product of the mass times the moment arm. That's some measure of the torque, kind of like what we did in lab. So this would be 1,000 times 1. This would be 1,000 times 0.5 or 500. This is 500 times 1. And this is going to be 500 times 1 plus 500 times a half, which is 250. Right? So we're looking for the most difficult, which is C. So we have C, D, and then B and A are the same. So that's E. Just measuring the torque, the total torque. All right, 2 buckets spin around. And I want to know what happens to them. We did a very similar problem when we were in chapter 5, I think it was, with momentum, where we had a cart and it had raindrops falling into it, which causes its mass to increase. And since its linear momentum is equal to mass times velocity, since its mass is increasing, its velocity is decreasing. A similar thing here. We have these water falling into these buckets. That causes the moment of inertia to increase, and as a result, omega will decrease. So that's A. The buckets slow down because their angular momentum is conserved. Moment of inertia is the rotational equivalent of mass. A rigid body is in equilibrium if both of these are true. The net force and the net torque are equal to 0. And rank these from the torques, based on their torques. Well, let's see. This one has 0 torque. So that C is going to be the smallest. And notice they're all listed as the smallest. You could go through and calculate these, and what you would find, this has a torque of 2 Newton meters. This has a torque of 1 Newton meter. This has a torque of 2 Newton meters, 4 times a half a meter. Oh yeah, I'm just taking all these to be 1 meter long. And this one's going to be 4 sine of 45 times 1 meter. And so that's going to be the largest. E is the largest. And then we have A and D are equal. And then B is next and C is last. So that's option A.